So these two are very special trajectories because they are along the directions of the eigenvectors, but we also have to draw more than this, like trajectories that start at other points outside of these lines. And I think it's easier to begin explaining this in a different case where one of the eigenvalues would be positive, like the ones we had, but the other one would be negative. In this case, we still have the arrows pointing out along the eigenvector of the positive eigenvalue, but along the other eigenvector, we are going to have arrows pointing in. And everywhere else, we're supposed to have things that sort of follow the same general direction. So this point here is not on the eigenvector, but it is close to it, so it's going to do something similar. As we get closer and closer to the other eigenvector, then that starts having more of an effect and the trajectory goes this way. So everybody over here would be doing something like this. And in this other quadrant, it would be doing this. We start by following this one, and then we gradually turn around and follow more in the direction of the other eigenvector. So the complete picture would look something like this for this case. Now, when we have two positive ones, it can be a little bit more complicated because if they were both positive but equal to the same number, then there isn't much of a mystery, right? All of the trajectories are just straight lines pointing outside from the origin. But if they were both positive but different numbers, like is our case in the question that we're solving, then all directions are going to be pointing out, but one of them is stronger than the other. So as we leave from the origin, there's going to be two possibilities. Either we start by going more in the direction of this one and then gradually turn around to the direction of the other one, and this is going to be going on in all of the quadrants of the picture. Or it's going to be the other way around. We're going to start by going out through this direction and then gradually turn around and become parallel to this direction. And I would try to avoid memorizing which is which because this is the sort of confusing thing that you can memorize wrong. Instead, I like to think of what's going to happen in the long run when t is very large. Because the y equals x line is associated with the zero point 0.2 eigenvalue, and the other line is with the eigenvalue 0.5. So in the long run, this one wins the bigger eigenvalue. The bigger eigenvalue pushes points more strongly than the smaller one in the direction of its own eigenvector. So in the long run, the directions are going to end up being parallel to this line, which means that they had to start from the other line. Another way that you can think about this is that if instead of two different positive eigenvalues, you had one positive and one zero, then in the direction of the eigenvector of zero, the trajectories wouldn't move at all. So everybody would be just parallel to the direction of the positive eigenvalue. And of course, they would be going out in that direction. Now, if you change that zero eigenvalue a little bit to become slightly positive, but still smaller than the two that we have in the other line, then there would be motion in the trajectories in that direction. It would everything be going out of the origin. But as you go from 0 to like 0.1, the picture can't change a lot suddenly. So it needs to look similar to this, which means that it's this direction that is going to bend first. So in the case of two positive eigenvalues, the trajectories start out parallel to the smaller one and then bend in the direction of the bigger one. You can also use this to think about the two different negative eigenvalues case. Again, if one of them was zero, nothing would be moving in that direction, so everybody would be parallel to the other one. But in this case, it's negative, so the trajectories are going in. Now, if you change that zero to something that is slightly negative, like negative 0.1, now everybody wants to go in, but the picture can't change a lot. It still has to have these sort of parallel lines. So the change is going to happen just here. Everything's going to start out parallel to the negative 2 and then bend in the direction of the negative 0.1, which is the smaller negative eigenvalue, like the less negative. And that's how we should decide in this case which direction goes first. And that's why I said that this case was easier with one positive and one negative, because then you don't have to think about these things. But I do need to say more about the two equal eigenvalues, okay? Because this case does not always look like the pink portrait in this picture. But the thing is that when we have two eigenvalues that are the same, we don't always get two eigenvectors like I may have led you to believe in the previous picture. So 1, 0, right? It is an easy eigenvector to sketch. It is the horizontal axis. And along that direction, the eigenvalue is 2. So it's positive, it's going outside. That doesn't really tell me anything about the rest of the picture. So what you're going to do in this situation is, let's write down the differential equation where this matrix came from. And now we're just going to choose a different point to look at, a point that we don't know anything about yet. Please pick the easiest one. This is the point 0, 1. And then let's just plug that into the system and see what happens. So we have both the x prime and the y prime being positive, so both coordinates are increasing, but the y coordinate is increasing faster. So at that point, we have a trajectory that points this way. And the way to connect the dots between the blue and the pink in order to make this into a phase portrait is that this thing came from here. It starts by going outside from the origin in the direction of the eigenvector, but then it turns around and comes back again, eventually becoming parallel to the eigenvector again, but somewhere else. This looks kind of bad. Let me try to make a better picture. And all of the other trajectories are going to do something similar. They're going to start coming this way, they're going to turn around, and then they're going to eventually go the other way. And the same thing happens on the other side, except kind of backwards, but always going outside. And I want to give you a little bit of an explanation of why this picture looks like this, because it's just so different from the other one that you can get with the same eigenvalues. Okay, this pink one is eigenvalue 2 with multiplicity 2, and this one is also the same thing, but the difference is in the eigenvectors. This one has two different eigenvectors and this one does not. So this is not the correct thing to be comparing it to. We should compare it more to this one, which has two different eigenvalues, and then we can think about what happens when they get closer together. One of them is gradually changing until they both become the same eigenvalue with multiplicity 2. So the example here is this matrix, which has one of the eigenvalues is always 2, with the eigenvector pointing this way, well, both ways, right? To the right and to the left, going outside because 2 is a positive number. And the other eigenvalue of this matrix is 2 plus a, which is giving us this other eigenvector here. The eigenvector is 1a, and the other one was just 1, 0, the horizontal vector. But as we make this a get closer and closer to 0, which is what I plan to do with the slider here, that a is going to go to 0, then this a is also going to go to 0. So the two eigenvectors will become the same. That's why we didn't have two different eigenvectors in that case. We're only looking at one trajectory here, which is this red one, but I think that's enough to understand. Look at what it's doing. It starts at the origin, going to the left, which is following the direction of the eigenvector. And then it turns around and bends in the direction of the other eigenvector. They don't really look parallel now, because I said here that this kind of thing eventually makes them parallel, but that's just because we're not looking far enough. If we zoom out here, we will see that eventually they get more and more parallel. Maybe you need to zoom out a long way, so for the purposes of the video, it's not good if I do this much. Let's just believe that they are going to be parallel. And with this amount of zoom, you can't even see the beginning of the trajectory, how it was actually following in the direction of the horizontal eigenvector, right? You can't see that from this distance. But look what happens when I make a smaller. See, the eigenvector is going down. It's getting closer to the horizontal. Its slope is becoming smaller because the slope was a. And you can also see the initial part of the trajectory more and more. I can even zoom out more here so that you see that it's still eventually going to be parallel to the second eigenvector. But the thing is that as a goes to 0, this is becoming bigger and bigger, right? It takes more time to happen, but it does happen. And when it gets parallel to the second eigenvector and a keeps getting smaller, then it's just getting parallel to the same eigenvector again, which is what we were drawing here. You can imagine that originally there used to be a second vector here, parallel to which these lines wanted to be, but this just became the same line horizontal. So that's the case that I think is the most complicated one, but we still haven't covered all of the cases, because when you get a 2 by 2 matrix and you find the eigenvalues, there's also the possibility that the eigenvalues are complex numbers. So in case of complex numbers that have no real parts, the trajectories are just going to be going around in circles around the origin. Sometimes they're going to be turning clockwise, sometimes they're going to be turning counterclockwise. And the easiest way to decide which one it is to just calculate at one specific point and see if at that point you're going up or down. Everything else needs to be following the same pattern. This is similar to what we did here to figure out the direction of this trajectory. Now, if the complex number has a real part and this real part is positive, then instead of just circling around and around, it's going to sort of spiral out, which makes sense, right? Because a positive eigenvalue wants to make things move away from the origin. And it could spiral out in two different directions. This is also positive real part. And again, to figure out which is which, just pick a point and see if it's going one way or the other way. If the real part was less than 0, then it's the same kind of trajectories, but they're just moving inside of moving out. So for linear systems, which is everything that we've been looking at today, which are the ones that can be written as a matrix, right? So the system of equations that they come from is always this system. The only thing that changes is the values of A, B, C, D. We have all of these interesting possibilities of things that can happen to how the trajectories look, but always around the origin. Interesting things never happen in other places. In order to have these interesting pictures happening in other points, you would need a nonlinear system. And it's a thing that I find very interesting to do, connecting the dots when you have more than one point with interesting things happening. So, for example, if this one is the one that everybody goes out, but that other point there has everybody going in, how can we connect the dots? What can the whole trajectory kind of looks like? Well, you can have one that starts here and goes directly there, but maybe this one needs to go out a little bit before coming back. This one needs to take a longer time to get there. And what about this one that's pointing completely the wrong direction? It's going to have to take an even longer path. So it's a very interesting exercise to put these things together and try to connect the dots, because it's not always possible. Like if this one wants everybody going outside and this one wants to go around in circles, then okay, you could leave from here and go that way, but now what? Now you are going to crash into this other one that came from there. So this is not possible. Some configurations work and some don't. If this one is going around this way, then maybe that one is the one that has one negative eigenvalue and one positive eigenvalue. Then in between here, the things are doing this, this, and this. But over here, this one does this, which matches perfectly with what the other one is doing farther away. But in any case, this is something that is very interesting, very pretty, but can only happen in nonlinear systems.